Good evening, everyone. For those of you who don't know me, my name is Boca. I'm the teaching assistant for this course. You can find my contact information under Brightspace, under the tab called TA Contact Info. Please feel free to reach out with any questions. And for those of you who haven't introduced yourself to me in class, please feel free to come up to me. I'm more than happy to talk about really anything related to the course. But yeah, so if you haven't seen my other videos, I typically just make video lectures on various topics that we go over in class. So one of the topics that we've been discussing a lot recently is matrices and the application to modern portfolio theory and Markowitz theory. So essentially, I'm going to make a three-part video lecture. The first part is going to be a review of matrix algebra that's necessary for this application. And then the second and third videos will be application to, two asset or n asset portfolios and optimizing these based on the mean variance. So the second video will be the actual practical calculations. Then the third video, we will be going into RStudio and actually writing the code for the optimization in R. So yeah, so let's just go ahead and dive right in to the matrix algebra. This is actually really useful, for various reasons, being able to have an array of returns versus, having to calculate each individual return. When we get to talking about the portfolio variance, it'll be clear why this definitely simplifies things, makes the formula look a little bit nicer. So yeah, these are really useful. And obviously, knowing how to calculate the optimal weights of various stocks in a portfolio is super useful. Even if you're not interested in financial analysis or working in finance for personal investments, if you have a certain number of stocks you want to invest in, right? Like Apple or Microsoft, you have to decide how much you want to allocate to each of those assets. And portfolio theory, which was developed by Harry Markowitz, is really useful for that reason. So yeah, let's just go ahead and dive right in. We'll start out with some of the simples. And for those of you that are familiar with all of these, you can go ahead and move on to the other videos. But I will say for assignment 4, this will be relevant for questions 1 and 2 on assignment 4. Sorry, assignment 7. So for those of you that are working on assignment 7 right now, this will be useful for that. So yeah, the first most basic thing we just want to go over is just adding matrices, right? So this is what a matrix looks like. This is a 2 by 2 matrix. The first number will indicate the number of rows, and the second number will indicate the number of columns, right? So there's 2 columns corresponding to that 2. And the important thing to remember for adding or subtracting matrices is that they have to be the same dimensions. So you can't add a 2 by 2 and a 2 by 3 matrix. That involves, some extra steps, but yeah, basically, they have to be the same dimension. So for these ones, right, if we were adding these, that's fine. These are both 2 by 2. So we can have the final matrix, which is 2 by 2 as well, just be the sum of the individual values, right? So 1 and 5, 2 and 6, 3 and 7, and 4 and 8. Where it gets a little bit trickier, I guess, is the multiplication, right? So with this one, you're basically just multiplying the corresponding. I guess that's, not as tricky, but yeah, just, for this one, what's important to remember is that the final matrix will end up being essentially the outside of the dimensions. So the final matrix of a 1 by 3 multiplied by a 3 by 1 will end up being 1 by 1, right? So that's where you get that. So essentially, this would end up being, right, 1 times 4 plus 2 times 5 plus 3 times 6. So that would end up being 32. And that would be our final answer. Yeah, so 14 plus 18, 1 by 1 matrix, right? So it's important to remember you're multiplying the corresponding rows by the columns. So column 1 by row 1, and yeah. So for the determinant, this is essentially just a single number to describe various properties of the matrix. Something that's important to remember would be that if it's 0, right, then it's a singular matrix. That means it's not reversible. So you're taking a 2 by 2 or a 3 by 3 matrix and you're making a single number out of it to indicate various properties about it. And what it means to be multiplicative, it essentially just means that the determinant of matrix A times B would be the determinant of matrix A multiplied by the determinant of matrix B. So that's what it means to be multiplicative. Yeah, so for 2 by 2 matrices, essentially these are the rules you're going to want to pay attention to for the purposes of our course. The beyond 3 by 3 gets a little bit more complex. You basically need to do cofactor expansion, which just gets a little bit tricky. It's definitely doable, but beyond the scope of this course. The 2 by 2 matrices and the 3 by 3 matrices maybe though, so definitely pay attention to those specifically, and especially the 2 by 2 matrices. This will be what most of our variance covariance matrices will look like for the finance applications once we get to those for the 2 asset portfolios. So yeah, basically the determinant of matrix A, which is 2 by 2, if these are the values A, B, C, and D, you basically multiply the first value by the last one, or the bottom right. So top left multiplied by bottom right minus top right multiplied by bottom left. That would get you the determinant of matrix A. For a 3 by 3 matrix, it's a little bit more complex. Basically, the way it works is you would hold one value's row and column, essentially, and then you would be finding the determinant of what's left over once you hold those constant, essentially. So you would take the value of A multiplied by the determinant of this box that does not include A's row or A's column, minus B, you're holding this row and this column constant, minus B times the determinant of what is left when you take these off, right? So that would be D, G, and F and I, plus C times, right, holding this constant, times D, G, E, and H, right? So you basically are taking a more complex matrix and breaking it down into a smaller one that you can then find the determinant of through the 2 by 2 method. So this would essentially be the most complex with regards to determinants that you would be tested on, but still very useful to know, especially these 3 by 3s when we get into larger portfolio allocations. So for the inverse of a matrix, this depends on knowing the determinant, right? So we would calculate the determinant first, and then once we know that, this formula will help us find the inverse of a 2 by 2. So essentially, you would do 1 over the determinant multiplied by you're essentially switching the first and fourth value and making the second and third negative. So A and D switch places and B and C become negative. And the 3x3, these are also a little bit more complex for the scope of this course. Depends on the adjugate. And so we're not going to go over those in this lecture, but if you are curious, you can visit this link, and that will show you, how to find the inverse of a 3x3. Okay, so now we get to orthogonals. And orthogonals is essentially the vector that you would multiply a given vector by to get 0. So essentially what that means is you're given a vector in the problem and you're asked to find an orthogonal of it, right? So it would be the vector that you multiply this vector by to get 0. So where the answer is 0. So we can say, let's say and I actually should have written this as a column vector. But let's say we're saying that this is going to be the orthogonal, right? X, Y, and Z, just random variables. And then for it to be an orthogonal, this given vector multiplied by the orthogonal must equal 0. So when we do that, we multiply these values out, we would get 0x plus 1y plus 2z equals 0, right? Just multiplying these out. And so if you solve that equation, right, you would end up getting y plus 2z equals 0 for this particular example. But basically you can solve for one of the variables, right? And then you're just solving it like a system of equations. So you're given, you solve for y equals negative 2z in this case. And then you can say, okay, let's suppose that z is a certain number, right? Let's say at a certain point, what are the values in the other? Because we know that we've set this up as an orthogonal. So if we just take one of the numbers as an arbitrary number, so let's say z equals 1, then we can find what y and I should have said x here. And we can say what y and x are, right? So if z is 1, then y would be, we plug it into this equation. So y would be negative 2. And x is a value that essentially it is independent of this. It can be any value for it to be orthogonal, right? Like changing x doesn't make this not an orthogonal vector. So, we can just say it's 1 or 2. So, the final vector, 1, negative 2, and 1, this last value, this x can be really any value. It would still be orthogonal. It would still be a product that would get 0. And then finally, the last thing that would be necessary for our prerequisites for this, just the eigenvalues and eigenvectors. For the assignment that you were going over, I just gave you the code for this. You can go ahead and plug in the values for the values that you were given in the matrix, the number of rows and the number of columns, and this is the function that you would use. So essentially just eigen C in R, that would give you the eigenvalues and the eigenvectors. I think I skipped a few actually. Let me go over those. Yeah, so the transpose of a matrix, this is essentially where the values become columns. The columns become rows and the rows become columns. So where you have a vector 1, 2, and 3, this essentially becomes a vector. The transpose would be a column vector of 1, 2, and 3. That's also important to mention. If a vector has 3 columns and 1 row, this is referred to as a row vector. So this would be a row vector, and this would be, if it has 3 rows and 1 column, this would be a column vector. Yeah, so the transpose is just switching the corresponding rows and columns. And the notation would be the letter with an apostrophe next to it. So the transpose of A would be A prime, or A with the apostrophe next to it. The trace of the matrix, this is essentially just the sum of the eigenvalues or the sum of the diagonal values in it. So if we have a 3 by 3 matrix, right? This would be 3 by 3. The trace is going to be a single value, which would be the sum of the diagonal values. So this would be 1 plus 5 plus 9, which equals 15. So that's our trace. Okay. And with that, we should be good. That should be all of the concepts that are necessary for portfolio optimization when it comes to matrices. Please feel free to reach out if you have any questions. This file will be in the link in the description. If any of you wants to track along with this or view this afterwards, please feel free to do that. Thanks for watching, and I'll see you in the next video. Bye.